For our project, we selected the following design requirements. It would be able to carry a max load of 2,000 pounds. It would have 1,000 life cycle endurance. For axial and bearing stresses, the safety factor would be 1.75 or greater. For buckling, tear out, and shear stresses, because those lead to catastrophic failure, the safety factor would be 2.5 or greater. The structure's assembly size would fit in a 1 foot cube space. Our goal is to minimize the mass, and through calculations, we selected that the angles of operation between the diagonal member and the crossbar would range from 15 to 70 degrees. This would provide a buffer to prevent extension and compression beyond the thresholds and avoid misuse.
Here are just a few of the models that we used while working on our project. In our project, we used free body diagrams. We used the method of joints, actually, to solve for the forces in the members. We analyzed the pins using the mathematical models for tear out, axial failure, for bearing stress, etc. We looked at the types of columns using this model. Ours turned out to be a Johnson column. We figured this would be about 1,000 lifetime cycle, and so we used this model to find the stress. Here we use the modified Goodman criterion to solve for safety factors. We used actual modeling in CAD, and we put our model into FEA to solve for the little piece in here. And then finally, we put everything into MATLAB.
Research process, we used this MATLAB code that we designed in order to test the various material properties that we'd come up with in order to find the optimal combination in order to minimize the mass. So we'd plug in the material properties here for the various members, the crossbar, the pin, and the diagonal, and we had our equations with the safety factors and forces, and then we'd calculate the max stress allowed for that failure criteria and come up with the minimum dimension allowed for the failure criteria. For example, here with the shear stress in the pin, we calculated the minimum diameter of the pin in order to protect against failure due to shear stress. So we did that for the various failure criteria as we were concerned about for the various members. And then we'd calculate the volume of the entire car jack with the dimensions that we'd come up with. And then we would calculate the corresponding mass. And we did that for various different material combinations. And we found the one that minimized the mass the most and still was within the required safety factors that we'd come up with. We then used the dimensions for the failure criteria that we came up with, and we verified the results by plugging them into a separate MATLAB code that Andy Avila in our group designed. That way that our results were verified by two independent systems in order to guarantee that they were correct.
So when it came time to look for what materials we were going to use for each of these parts, we largely just used McMaster-Carr and searched around for either a similar part or one we would actually use, and McMaster-Carr was really good about listing the exact alloy of steel or aluminum that they were using, and we could figure out the material properties from there.
We learned a few good lessons from the design project. The first being, when you're creating a design, make an educated guess about the initial conditions and iterate from there to find out what else you need to change. What we did was start with a maximum angle that we felt would be good to not put the lift under extreme stresses. Another lesson we learned is the diagonal member cross section isn't extremely critical. Because it's not subjected to bending stress, the cross section and the moment of inertia of it doesn't matter as much. Another lesson we learned was the FEA analysis in Workbench is extremely important. We analyzed the pin that would hold the crossbar and the members together and found out that it would fail if we actually implemented it. So we had to change some geometry on that. And one last lesson is the MATLAB code is just extremely important. Here you can see we can change all the initial conditions of the material properties, and through that we can run the code and it'll allow us to iterate very quickly.